Yes, so actually I'm going to talk about things that I don't do at work. So basically all of what I'm going to talk about today, or most, like 95%, is on is in free time. I'll come back to the backgrounds in a second. And the topic is that is basically on getting root, or all the components that root needs, in particular LLVM, jitting, Cling, and Clang REPL, working on RISC-V, so the new architecture that some of you may have heard about. So I'm going to start with a bit of context just to introduce RISC-V and root is, but I guess so especially what root is, I think many people already know. I'll try to keep it short and then actually go to the journey of bringing up the stack in order then in the end to arrive at running actual physics analyses and hopefully finding the Higgs. Yes. So what is RISC-V? Or let's start with what is RISC. So RISC stands for Reduced Instruction Set Computer. So the opposite of this is the CISC, so Complex Instruction Set Computer. Prominent representatives of CISC are, for example, x86, and prominent representative of RISC is ARM, as is used as an architecture in smartphones up to supercomputers. The Japanese Fugaku, for example, uses ARM. So what is RISC-V? RISC-V is the fifth generation of RISC architecture from the University of California, Berkeley. So they basically had 4 preceding RISC architectures that they did over the couple of over the years, over the decades. And what is really, I think, really new about RISC-V is that all specifications are open source. So everybody can read them for free. Everybody can contribute to them. There's, of course, an overseeing standard committee in order to make sure that everything is coherent and so on. But they are free to read. They are free to contribute to. And most importantly, the instruction set architecture comes without licensing fees. What this means basically is that every hardware vendor that wants to can take the specification of RISC-V and implement it in hardware. So they can create hardware without paying any licensing fees to any party. That's a big difference compared to ARM, for example, where you have to pay licensing fees to ARM. And the main purpose, I mean, originating from the University of California, is also that this is a nice property to have for research, because now you can actually start playing with it, do it in your research, and not pay licensing fees to corporate, to big companies, which is really nice. The second big thing about RISC-V is that it has a modular design. I'm not actually, so this also kind of exists for I think ARM, where they kind of add instructions over the time. But for RISC-V, they really did it from the very beginning. So there's basically a base integer instruction set. So RIV32I is the RISC-V 32-bit integer instruction set that has only 40 instructions. So you can actually go read the document and understand all the 40 instructions, and then you know everything about what is there to RIV32I. Then there's RIV64I, which is basically the 64-bit extension of this. It's adding 15 additional instructions, because you can load bigger, so 64-bit values, and then you can shift 64-bit values around and so on. But in total, this is a very small base architecture set compared to other architectures. And then what they are doing is that you have extensions on top of these integer instructions. So there are extensions for integer multiplication, for atomics, for single precision floating point, for double precision floating point. And they are abbreviated by what I marked here with bold characters, so MAFD. And because that gets a bit cumbersome to always spell out those letters, there's actually an abbreviation, so you can call all of this. So IMAFD is equivalent to G, which stands for general, because this is what the hardware architecture thing is, a reasonably complete set of instructions to run a general purpose operating system on. As is usual, I think, for RISC architectures, is that all instructions have the same length, in this case 4 bytes, except the compressed instructions, which is actually yet another extension of the ISA. Those compressed instructions are only 2 bytes, and they are basically trying to cover the most important cases of instructions. So the most used instructions you can hopefully express as compressed instructions and then save code size. That's the idea. But that's only the tip of the iceberg. There are actually more extensions, some more which start with a single letter, some more standard extensions which are starting with a Z, and then actually also a vendor can decide to implement or to create custom extensions, which are then by conventions will start with an X and then some description of what it is about. So, for example, if a hardware vendor wants to invent new instructions for, I don't know, compression, compression as in zlib compression or whatever, then they can do so. They can just use basically reserved space of the operation of the op count in the instruction, and then define a custom extension that they can implement in their hardware. So why are we here today? So the reason is that in April 2021, so just to mention, so RISC-V, I think, was created in 2010, so it's a relatively new architecture. And in April 2021, last year, was the announcement from the RISC-V International Corporation, which is basically which is an umbrella for a non-profit umbrella for maintaining the RISC-V specification. They announced that they want to distribute up to or over 1,000 boards for testing and development of open source software, with basically the only requirement that you have to provide monthly status updates in a Google Doc, and that you have to provide that you have to be a member of RISC-V, which for individual members actually free. So you can just go to a website, you can click, I want to become an individual member of RISC-V, and then you have to agree to some documents, and then it's free. So I did this. I became an individual member, and I submitted an application, project application, to get a board. And unfortunately, I didn't get one in the first round. So then I basically forgot about this until I got an email in March 2022, so almost a year later, that there is going to be a new round of development boards and that my project application was chosen, and if I could please confirm if my address is still correct. And you'll see you see the technical data of what this board actually has. So it's called it's by StarFive and called Vision 5. It has a dual core from SciFive. So SciFive is basically selling the intellectual property for cores, and U74 is one of them. A dual core with 1 gigahertz. So as you can already see, you should not expect like incredible performance from this thing. 8 gigabytes of memory and all of the standard extensions. So you have HDMI, USB, Ethernet, Wi-Fi, Bluetooth, and a 40-pin GPIO header. And then eventually in May 2022, the board arrived. And this is what it looks like. And now I'm going to stop. And I'm actually going to show it to you, because I think that's nicer. So this is what it looks like. I actually got a kit. So that included this fan, which is supposed to be plugged in here, but that's too loud. So you just plug it into I plug it into the GPIO pin header at 3.3 volt instead of 5 volt, and it's much less noisy and much more agreeable to be in the same room with. And yeah, you have the standard connection. So you have Ethernet, you have HDMI, 4 USB slots. You have USB-C for powering, and yeah, a micro SD card for storage and operating system. So yeah, it looks pretty much like a Raspberry Pi, and I think even the GPIO headers is even compatible with Raspberry Pi. So I'm going to put this away again and actually plug it in so that I can maybe do a demo later. Let's see if that works. Okay, I think I should be back to sharing. So just to finish off the context, LLVM is a reusable set of libraries for compiler toolchain, and the important part for Clang REPL, Kling, and Root is that it also supports just-in-time compilation. Kling then is the interactive interpreting of C++ using Clang and this LLVM JIT that I just talked about. And Clang REPL is upstreaming parts of it into the LLVM project that Vasil just mentioned before. And Root is the framework for data analysis. And for example, or in particular, it is used in high energy physics here at CERN, and is making use of Kling for fast prototyping, but also in the internals of, for example, our data frame. I come back to this for finding the Higgs actually. So that's for the start. So now let's build up the stack, or actually start with reviewing what was already there when I got the board. Because the usual approach for porting to new architecture is that you start bottom up. Of course, you don't start with the high-level applications and whatnot. You of course have to start very close to the hardware, and starting very close to the hardware, of course, or at least in this case, is the Linux kernel that already worked. So it's not the upstream Linux kernel. There's a fork with patches and drivers and whatnot. That worked reasonably well. I still submitted, I think, 2 patches to this fork to fix some minor things, but overall was running pretty stable. On top of this, you can use Debian, for example, which has an up-to-date RISC-V port. So Debian unstable, basically everything is also built for RISC-V. And Debian, you get a lot of access to a lot of pre-built packages already. You don't have to recompile everything, which is very nice because you can start right away. You also get compilers. The compiler support for RISC-V are in a pretty decent shape, I would say, both GCC and LLVM Clang. So in total, everything set for bringing up root, with the idea, of course, to try submit patches to the upstream projects as much as possible, because everything that is upstream is also going to survive and being available to everyone. So building up the stack, the next one that we have to talk about is LLVM. As I already mentioned, the compiler support itself is in a pretty decent shape. Code generation is, I think, basically complete for the base instructions and all of the standard extensions. There's, of course, optimization work ongoing and support for other extensions. For example, one extension that I didn't mention yet is the vector extension, which is aimed for high performance computing, for example. That's still ongoing, but all the base integer instructions and all the standard extensions that you really need for running general purpose applications is already well supported. And I was also very pleasantly surprised that JIT support also already exists. At this point, huge thanks to Steffen Luxu Fan who did a lot of fantastic work, I think, in LLVM upstream already to contribute a backend for JIT link. which is, yeah, I think it's fair to call the newer generation JIT linking infrastructure instead of the legacy runtime DYLD. So actually, in this place, there wasn't much to do. The only contribution that I did is that LLVM now defaults to using JIT link on RISC-V, the same way that it already defaulted to using JIT link on macOS. So that actually now LLI, which is the LLVM interpreter, will work out of the box. So there's no more. So before this patch, you had to basically supply a whole bunch of command line flags to this LLI command in order to make this work on RISC-V. So now let me try if I can. Can you see this? Is this reasonably okay large for people?
It works for me, maybe a bit up. One more, no, too much.
Okay,
yeah.
This should be fine, right? I mean, I'm not going to code anything. It's just that I want to show that it's actually working. So as I said, I plugged this in basically in Ethernet, and then you can just SSH in. You're running with the Debian unstable, and you have pretty much standard system. So you have apt, you can install packages, and yeah, for a start, this is just a hello world C file, nothing very fancy. Then I can just call Clang on that. Yeah, as I said, it's not the fastest one. Then you get out the LLVM IR in text form that you can read, and then we can just use LLI to interpret this and get our hello world back. Right, so let's go back to the presentation. So moving one step up, the next part is, so LLI works. So now the next thing is to get Clang REPL or C++ interpreting working. And another big surprise that Clang REPL basically worked out of the box. Well, there was one caveat, is that it complained very loudly, so warned very loudly with this warning message. So the hard flow D ABI can't be used for this target. It doesn't support the D instruction set extension. You might remember D stands for double precision. So what it basically complains about here is that, or this is basically has to do with RISC-V's modularity in extensions. And this is only going to be the first time. There's going to be a second time in this presentation where we are going to have to deal with this. So what it's complaining about is that some part of the Clang REPL thinks that it can use the D extension, and some other part, in particular the LLVM backend, is not aware of this, and then complains that the front end tells it to use an ABI, which requires the existence of the D instructions, but it's not aware that it's happening. The solution is actually pretty boring. What you have to do is that the Clang front end and the LLVM JIT target machine in the back end, they have to agree on what target features the generated code is going to use. So there's so all those Ds, the D and the number are linking to LLVM reviews. So this is what I sent upstream, and all of this, what I'm going to show today, is already committed in the repository, so it's available for everyone with very new LLVM releases. Unfortunately, if you do this, then you not only get the D instruction set, but also, because Clang on Linux defaults to assuming the C instruction set, so the compressed instructions, you also get compressed instructions and linker relaxation. I'm not going to talk about linker relaxation in more detail. in essence, all of this leads to additional relocations being emitted. So what is a relocation? Relocation is if the compiler, during compilation of an object into object code, doesn't yet know, for example, the address of an external function, it emits a relocation so that later on, when this information is known, the appropriate address can be filled in. This is very standard. This is exactly what the JIT-link backup, or what JIT-link is about. This is, for example, for handling these relocations, and by enabling the compressed instructions, we actually get more of them. Fortunately, those two that are added here are only for code alignment. And in some circumstances, and we are in those lucky circumstances, fortunately, they can be ignored. So you just have to do some checks if the code is aligned enough, basically, and then you can ignore those relocations. So that's what I did, and then everything is working. Let me show you. So that I don't forget what I want to show. And we can start Clang REPL. And then we are basically at the prompt, and here we can enter C++ code. So we can say, and also C code. We can include standard IO header. We can use printf. We can include some more, which gives us the machine architecture, which is indeed RISC-V. But we can also do more here. We can also include vector. Then we can construct a vector of integers. And then we can hopefully push things to this vector. So basically, this is Clang REPL working without a lot of work, I have to say. All right. So next step, moving one step up. So Clang REPL, as I said, is the upstreaming part of parts of Cling into LLVM. So I decided to go for this one first because I suspected, and indeed I was right there, that this would be the easier target to bring up first. Also, it allowed me to stay with LLVM main, so I could immediately benefit from everything that other people already implemented there. And if I had to make changes, the two changes I already mentioned, I could send them upstream immediately and not have to worry about different older LLVM versions. So for the next step was Cling, and actually I didn't go for Cling standalone, but I actually decided for kind of a minimal version of root. The problem, in quotation marks here, was that at that time root was still using LLVM9. LLVM9 didn't have the JIT-link backend for RISC-V at all. So it had some backend for macOS, but nothing for RISC-V. So instead, I was actually for my work at CERN, I was also involved in the upgrade for LLVM13, and LLVM13 had the base work for the JIT-link backend for RISC-V. So basically, I just took a random commit from July when I started trying to bring up Cling, created a local RISC-V branch, and then started working from this on LLVM13. And again, for bringing up, I took a very similar approach to what I described before. I started with building with -d minimal on, which basically disables everything that is not required to run like a minimal version of root. And then started making that build. So added the build system. I'll come to that in a second. And then once the current version was working, I successively enabled more parts of root to get a more and more functional build of root. At least that was the plan. In November, December, something wasn't working. I also come back to this. And I decided that, yeah, well, I actually don't really care about this one working, but I want I wanted to go to the physics analysis. So I started trying to enable the data frame build option before I had this problem figured out. I can tell you this didn't go well. So I should have better kept to the plan. That would have solved me some weird debugging, or at least wondering what the problem could actually be, while it actually turned out to be the exact same problem as I had before. So what was actually needed to bring up root and cling? So first, you have to add support for RISC-V to the build system and the configuration. Of course, the build system and configuration need to know that there is a new architecture. What are the properties of the architecture, that it's little endian, and so on. Then what I figured out pretty quickly is that LLVM13 was missing many relocations and also some jiggling features. So actually, a lot of the initial work was finding those commits upstream in LLVM main and backporting them to my local RISC-V branch based on LLVM13. And one thing that I would like to mention here especially is because I think, Lang, I saw you connected. I at some point had a problem with generating code, including exception handling. And this was actually solved by Lang upstream. I'm linking the commit here. So I just took this, applied it to my LLVM13 branch, my RISC-V branch, and could move on. Of course, I also had to work a bit myself. So I had to implement 2 relocations related to compressed instructions. So those are now properly implemented and will be released with LLVM16. So this revision is only, I think, 2 weeks old. And just to show you what this is about, please don't get too scared here. So these are the two relocations. So REC stands for RISC-V compressed. And then there's a branch relocation and a jump relocation. And basically what you're seeing in the middle here, these extract bits, they are extracting the noun value. Of course, during runtime, you know the value that you have to write for these relocations. And then because of the way that the RISC-V instructions are built up, you have to put the right bits into the right places. So this looks a bit hairy. Actually, this is only writing, like looking at the RISC-V spec, figuring out which bits to extract, at which positions to shift, and then assembling everything together into the instruction and writing it back into memory. So it looks a bit more scary than it actually is. So this one I did. Actually, one mistake I made here, and that's caused me a lot of problems, is that I actually made a C++ mistake. So I forgot this break from the first relocation. I can tell you this didn't go too well, because then it was, whenever there was a RISC-V RVC branch relocation, it was also processing the thing as if there was a RISC-V jump relocation. So actually, it wasn't like, it was working in some cases and was not even crashing in some others. But it did crash in some, and it was really hard to debug, because at some point I just printed out what I had assembled here, and basically tried to check this by hand, and it was working out, only then to get overwritten by the second one. Yes, I would have caught this with test cases. At that point, I didn't have test cases. After I found it, I wrote test cases, so hopefully this will never happen again. All right. Another issue that I had was with constructing global C++ objects. So whenever you construct, as I did in the demo, when you construct, for example, a C++ object, state vector, for example, then these are obviously constructed, and they are registered to be deconstructed or destructed with the add-exit handler, which is intercepted by the JIT or by the executor. And the problem here was that for the JIT to know, or to basically find back to its own data structures, we are using the DSO handle special symbol. which usually refers to the shared object, and Clang, because it can do so, marks this as local. So it assumes that it is in address space very close, and then LLVM takes advantage of this and basically tries to use the wrong relocation. And this was causing problems because then I basically got the wrong pointer back to the JIT, and then everything was crashing on me. Fun fact, I debugged this in, I think, October or so, and we hit the exact same problem 1 week later on macOS during the LLVM 13 upgrade. So this is for now worked around in Cling. I still have to think about whether it's the right place to do it, or we should actually be doing this in JIT-Link itself. Yeah, and then final problem was that constructing a TH2 did not work, which unfortunately is done by the H-Simple tutorial, which is run as part of the root build process. So actually my build process wasn't running through. And the error was actually very weird. It was complaining about invalid arguments. I looked at the source code. The argument that I was passing were correct. So at some point, I was looking actually at the register state, and I found out that the register state was not what I expected it to be. And here we come to the second part of RISC-V modularity in practice. What was happening is that the LLVM code generation was choosing the wrong calling convention. So you remember that in the base ISA there are only integer instructions, and consequently there are no floating point registers. So of course, for passing floating point values in these calling conventions, you do it differently depending on whether you have floating point registers or not. So actually what was happening here is that the LLVM code generation that was choosing the calling convention, again, wasn't aware that we have the D extensions, wasn't aware that we have floating point registers, and then all arguments were passed in the wrong places, and there was basically a mismatch between what the JIT compiled code put into the registers and what the library code that had the TH2 constructor was expecting to be in what places. I have to confess that I don't have a satisfying solution for this yet. This was at the end of last year and really wanted to get it working. So for the moment, I just hacked the default calling convention to be the one with floating point registers, because I know this is the one that root is going to use. Probably it's going to be the proper solution, or the proper solution for sure is that this the target features have to be passed down to the correct place. I just haven't found the correct place yet, but this is still on my list. But for now, it's hacked in order to get it working. And by getting it working, I mean that the C++ REPL works as expected. The only exception being that throwing and catching exceptions is a bit of a problem. So when catching exception would need the unwinder to go through stack frames that have been JIT compiled. This is currently not working properly because those stack frames in the JIT code are for RISC-V right now not properly registered with the unwind library. I know where to fix this in principle. I tried it. It didn't work out of the box, so I decided to leave this alone for now. But yeah, that's the current limitation. So for now, whenever you throw an exception that needs to go through JIT code, you basically end up with a crash of the interpreter. Not very nice, but yeah, we have had the same situation with Apple on Apple Silicon for a while, but at least here I know how to fix it. So that's on the to-do list. So let's see this in practice. So I'm going to start root. Right, so you root interpreter starts up, gives you the banner, and then gives you the REPL. And there we can exactly do what we have already been doing, or what I've actually already showed with the Clang REPL. We can create a vector. It's not properly working with everything. We can push back a value. Then we can use the value printing in order to print things out. Then we can push another value. We can print it out. It's all working. We can from here on use everything that you're kind of used to with root. So you can create our data frames, you can create TH1s, you can, and so on. So this is basically working as far as I tested. I didn't test a lot in order to not find too many problems, but for now I'll claim that it works.
Maybe one element for you, new T browser. Did you test that?
No, because I haven't enabled that one.
Okay. That's combining like a lot of features, and that's something that I used to test when we were migrating to Flink.
Yeah, so actually one of the big challenges or one of the bigger things that I had to enable at some point was actually X11 dependencies, because I wanted to get PNGs, and for PNGs you need X11 support compiled into root. So that was already, I can tell you it's taking, like, as I said, this thing isn't exactly fast. So every compilation that you do, and root I'm building natively on this thing, it's taking a lot of time. So yes, I'm going to try in the next time I'm going to try and enable more features of root and see how it goes. Yeah, but good point actually that the root browser is probably stressing a lot of parts again. Okay. Yeah, so what you can do with root, you can also run physics analysis with our data frame. So this is, you have to trust me because this one is actually taking too long for me to show live. So this is the data frame 102 tutorial, nano ALD analysis for 2 muons, and then the reconstructed mass. So I'm not a physicist, I can't explain you what this thing is doing exactly, but this is the picture that you get out of it, and you just have to trust me that this is actually something, or this picture is actually something that I produced running on the RISC-V board this morning. So this is exactly working as expected, so you get out a PDF file, and good, and then you're good. And now we're actually coming to the last step. So this tutorial I ran with the C macro. So basically just passing this to root. And for the final step, I decided to aim for the data frame 103 tutorial, which is a Higgs analysis. And actually I decided to go for the Python version of it. So this is of course still a simplified, but still pretty complex analysis written in Python. It is interesting, or I found it interesting for testing, because it includes a C++ header file to JIT a number of functions. So you have Python, including a C++ header file, and then using our data frame define and filters using those JITted functions in order to do the actual analysis, and then eventually run the event loop on the input data. So this tutorial is running on open data recorded in 2012 by the CMS detector. And a very important part here is that it uses a pre-skimmed data set. So it's already pre-filtered, which is very nice because it results in a reasonable runtime in the order of minutes on this RISC-V thing, so that you can actually not wait like entire days for this whole thing to run. Yeah, and now comes the plot that I've promised in the title. This is what you get out of this data frame tutorial from Python. And yeah, there is the peak at around 125 GeV, which, according to the physicist, is consistent with the Higgs boson. Yeah, so this plot, again, you have to trust me. This one is actually running a bit shorter, but maybe if we have time, I can show this live, that it's actually running. but this has been produced also this morning on the RISC-V board itself. So it just SSH'd in and then copied out the resulting PDF and included it into the presentation. All right, so conclusions. A lot of stuff is working. So what's remaining work? The first thing is that I said that I'm running on a commit from July. During the very last days of the LLVM upgrade, we disabled JIT-Link support during the LLVM upgrade due to some problems we had. So this has to be properly implemented again. This was on me anyway, for my CERN work anyway. So there's already a draft PR up that I uploaded this week. After that, I'd like to try rebase my local RISC-V branch on top of master, so that I get the final state of the LLVM upgrade and everything, all the fixes that we implemented over the last month. And then hopefully this will allow me to extract the build and configuration changes and submit this into root master itself. Because then the hope is that basic support on RISC-V should come basically automatically with a future LLVM upgrade, because all work that is needed in LLVM I have already upstreamed and will be released with LLVM 16. So if root is upgraded to the LLVM version, then it would automatically work on RISC-V as well. And I've already mentioned this. I think adding support for exception handling in JIT code. I know in principle where to do this. I think I also know what I have to work on for that. What's not yet there, but that's still on my to-do list. I just wanted to get to this point before investing more work into this. So summary, actually have to mention this again. LLVM for RISC-V is in an excellent state. Both the code generation and also the JITting support. It's really nice. Was really a lot less work than I had initially expected it to be. Fling and root are functional on RISC-V as far as I tested so far. We can even run analysis with our data frame and even with Python with PYROOT. And of course, we found the Higgs. So yeah, thank you. That was the presentation.
Thank you, Jonas. Really impressive. Congratulations. Questions and comments? We have 5 minutes for questions. Maybe I can start with one. So you talked about JIT-Link and quite a bit, but is the support like solid in terms of produced code? Do you have a chance to look at the quality of the produced machine code? Do we translate RISC-V in an optimal way?
So I mean, so JIT-Link itself is not about the producing of the code, I think. I don't know if Lang is still connected.
He had to leave.
Okay, so JIT-Link is about these relocations, and actually, I know that we are not doing the optimal thing. So this linker relaxation that I mentioned at some point is basically a way for the compiler to tell the linker, look, if this function is close by, you can actually replace this amount of instructions by a shorter sequence of instructions. This is very tricky. I have not attempted to do this in JIT-Link. I'm not even sure if there currently would be enough infrastructure to implement this in JIT-Link. So this is currently not done. As for the code quality coming out of LLVM for RISC-V, I have no, like, also because the hardware that I have is very, very weak. I don't really know how optimal that already is. As I said, there's ongoing work for generating basically better code by people who are working with the hardware designers, who are telling them, look, if you generate this and that code in this and that way, then we can execute it faster. So I think I mean, don't have to forget that this is still a very relatively young architecture. So I would still assume that there is still a lot of way for improvement there, especially in terms of performance. But in terms of functionality, I think it's very solid already.
Okay, thank you. More questions?
I have a comment and question. So in the past, we tested our Alpaca framework, which is abstraction framework for different processor architectures, also on a RISC-V system. It was a precision of this system. And we had some benchmarks and found out that the performance of the RISC-V system was about a half of a Raspberry Pi 4. But luckily, like Jonas already mentioned, so the software infrastructure was quite good. So it worked out of the box. Compared to ARM version of Rasputin, it was not so nice. And so, but some point which I thought about at this point was to do cross-compiling. And Jonas, did you already think about this possibility?
Yes, so actually that's the thing that I'm doing. So I mentioned that I'm compiling root natively, and it's really a pain. So compiling the entirety of root, I think, takes more, so even the minimal version that I compiled, because it has to compile all of LVM13, I think it takes a total more than a day. That's not very convenient, I can tell you. So actually, what I'm doing for my LVM and the Clang REPL work, I'm actually cross-compiling this from my powerful Ryzen machine, and then just copying this over via SSL via rsync, simply because it's more convenient to have copying the binaries over is still a lot faster than native compilation on this thing. I guess this is going to improve, but I didn't want to attempt root cross-compilation. I think that's not going to go too well.
Yeah, but on the other side, it's pretty stopping from development. So for work, we also decided only a workstation for compiling Cling. So I can feel your pain. My record was only 2.5 hours on the old Sandy Bridge system with 2 less SSD and RAM memory.
Yeah. So I mean, you have to keep in mind. I mean, so I think this one is even slower than a Raspberry Pi, and a Raspberry Pi is already not that fast. So yeah, you have a dual core, 1 gigahertz, pretty early version of an architecture. It's not yet like fully optimized by the hardware designers. So actually expect and already know that newer generations are going to be a lot faster. But for bringing up things, it's already very sufficient, I have to say.
Yeah.
Okay, thank you. By the way, because you said a little or big endian, is RISC-V little endian?
Yeah, it's little endian. It used to be only little endian. Then in the last round, actually preparing for the talk, I figured I looked again into the standard, and I saw that they actually added the possibility of having big endian. I know why, because they say that for networking applications, which is so networking is big endian. They also wanted to allow RISC-V running in big endian. I hope there will never be Linux machines running on big endian RISC-V. If not, I think we have to find the people who are responsible for this and tell them that they should not do this. So for now, we can assume RISC-V to be little endian on Linux at least.
Okay, yeah, I was hoping to hear it's a little endian only, but yeah, that's a lot of fun.
So actually it's pretty funny. I found out yesterday that so the RISC-V spec now supports systems with big endian, but actually the instructions have always to be encoded in little endian, for the reason that where do I have it? So all instructions are 4 bytes, so that's easy to decode, but compressed instructions are 2 bytes. So in order to figure out if an instruction is 2 bytes or 4 bytes, you have to look at the right thing. And at least this is guaranteed by the spec. This is always going to be little endian.
I think we have time for one more question. Okay. If not, I would propose to stop